Hello, everyone. My name is Karamo. I just currently graduated from the Thai Medical University in Taiwan, Master's in Medical Informatics. So I would like to share with you the current research that we just finished in our research lab to present my findings with you all. The title of our paper that we just completed is about leveraging muscle learning to predict liver cancer risk in overweight and obese patients using one of the hospital data in Taiwan. So this picture is myself, Karamo, talking to you right now. Okay, so the general introduction about liver cancer is that it is one of the problem in Taiwan, especially for elderly populations. Although our study do not only span on the elderly population, we are only examining the youth, where those who develop obesity and also those who have overweight. So before we conduct this study, we did some literature search to see what have been done with associations of liver cancer and also obesity and overweight. So we found from literature that there were studies done on non-alcoholic liver diseases relation to liver cancer, and there are other studies that were also conducted using nasal steatohepatitis to liver cancer and also cirrhosis. So from the literature, we found that cirrhosis was more of the hepatitis B virus and the hepatitis C virus linked to liver cancer. So our study wanted to explore what's going to be associations of liver cancer to obesity, because from literatures we found two studies that works on these associations, and one was a meta-analysis study which did not actually go further to expand on their relationship, and we also found a study that was conducted using traditional statistics to explore this relationship between obesity and that of liver cancer. So our study wanted to use more advanced AI technology, which is the machine learning, to see if we can develop a model to produce a better performance to predict patients with liver cancer that has obesity, overweight. So the reason why we do this study is that we explore one of the common cancers in Taiwan. All the picture showing here is that these are various types of cancers which are associated with overweight and obesity. And in Taiwan, all these cancers here are present. But the most emphatic one is the liver cancer. That's what our study is based on. So our problem statement spans from liver cancer. Why is this a problem in Taiwan? And what is the need for us to conduct this study? So from the literatures in the studies done in Taiwan on different kind of cancers, liver cancer happens to be one of the top diseases in men and the second in women. And generally, cancer is one of the leading causes of death in Taiwan. And the cancer that we have in Taiwan, most of the attributable risk was from hepatitis C virus, which currently there is no vaccine available for it. And we also have the hepatitis B virus. For hepatitis B, there is a vaccine for it in Taiwan, for the elderly, for the young children, and also for the youth. And now, after all this is come from different literatures, now we also know that etiology of different kind of cancer, which is not attributed to hepatitis B and hepatitis C, could be caused by different factors. And these factors are unknown currently. So different studies are doing in order to see what are some of the factors also contributed to liver cancer stage in Taiwan, apart from being hepatitis C and also from hepatitis B virus. So the goal of our study was to develop a machine learning model. So the model that we want to develop is XGBoost. XGBoost is one of the machine learning models that currently just spawns up. And then many people have been using in their study to compare with the traditional machine learning algorithms to see how it performs in predicting a specific task. So our goal is to develop this model to establish a 1-year risk prediction model using the clinical data. So in other words, we wanted to see patients with obesity and also with overweight in 1 year, what is the risk of these people developing liver cancer? So we're going to develop a model that will predict and give us a better performance. And then apart from the goal, apart from the aim that we have, the objective that we wanted to explore is we wanted to compare our model that we developed, which is XGBoost, to one of the common models, random forest, and also logistic regression. Because logistic regression is not by naturally or by convention is a traditional method, but we will incorporate it in machine learning and also with random forest, because these are two common models that are already been used in AI field. So the models that we wanted to develop, we're going to compare this model to this and see whether we perform better random forest and that of the logistic regressors. And also, we wanted to identify what are some of the most clinical features that contributed to liver cancer in patients with overweight and also with obesity. So these are the aims and objectives that we wanted to explore in our current study. So what is the clinical usefulness of our current study? First, we wanted to fill gaps in literatures about liver cancer, how it associated with obesity and also with overweight. And the second implications of our study that is that we also wanted to facilitate the early intervention and improve patients' outcomes and also provide a synopsis or prognosis of patients with liver cancer who have already been risk of having overweight and obesity. And finally, our results from this study could also influence current medical practice and also provide care guidelines that could help improve patients' outcome and also give some recommendations to the physicians in managing patients with liver cancer. So the definition for criteria of our study, because when you look at obesity, is actually a multisectorial. The WHO have a definitions for obesity and overweight. The Taiwan Department of Health also have their own definitions for obesity and overweight, and also the WHO ASIN criteria for obesity and overweight. So the first criteria here implies that even those in the Gambia is the world's definition for obesity and overweight. So in the Gambia, if you are conducting study on obesity and overweight, you can use these definitions to enroll your patients. So if you're specifically looking at Taiwan context, you can develop this because people believe that the Asians' waist circumference, their height, and also their weight is a little bit different, especially for those in Africans. So because of that, Taiwan Ministry of Health developed their own threshold criteria. And for this one is the WHO ASIN criteria. So why do we use this in our study and not this one and not this one? So when the presentation goes further, I'm going to give reasons why we use the WHO ASIN criteria instead of using just the Taiwanese data, because the study or the data we use from this study is from Taiwan. But instead, we decided to use the WHO ASIN criteria instead of using the Taiwan Department of Health data. But what is the reason? We will get to know when we go to the methods. Okay, so what are some of the methods applied to this study? First, this is the data wrangling steps that we conducted before we developed the models. First, the data was acquired and it was pre-processed. So the data was from the MJ. MJ is actually a Chinese name, major database. This is one of the Taiwanese hospital registry database, and this data was acquired from this hospital. So the reason why we use when you go back here, the reason why we use the WHO ASIN criteria instead of the Taiwan Department of Health definition for overweight and obesity to enroll our patients is because when we first explored the data, we examined how many patients were from Taiwan. And then we also explore how many patients were from Asian countries, not Taiwan. And we also explore how many patients are from different parts of the world, excluding Taiwan and also in Asia. So from our analysis, we realized that 90% of the study population are Taiwanese from Taiwan. And then 6% of the study population here are from other Asian countries, Hong Kong, Indonesia, and so on. And then the remaining percentage was from the other countries. So based on this definition, we realized that if we want to develop a model specifically focusing on the Taiwanese definition for obesity and overweight, then that means this will create some little form of bias in our study. Instead, we're also trying to use the Asian criteria so that those from different Asian countries will also have a subset clue on findings. And in other words, our study can also be generalized to different countries in Asia because the method we used was not only specifically for Taiwanese populations. Although this might not create a lot of big marginal difference if we continue using the Taiwanese definition because the threshold between these two is very, very small. So for the feature extractions, so before we start the study, we look at the clinical database and we realize that we have a lot of variables in the data. But our study is about obesity and liver cancer. So that means the features or the variables that we're going to use in our study should be to liver cancer. So because of that, we asked a medical doctor who is specialized in liver cancer research. And then this expert gave us some guidance on what are some of the variables are related to our current study. And also we did a domain knowledge. So the domain knowledge here is to do a literature review and see what kind of variables different studies are using when they are doing studies on liver cancer problems, either liver cirrhosis, liver fibrosis, hepatitis B, and so on. So after we confirmed these two, then we did stepwise logistical regressions. But how does it work? Because after the experts have gave us the guidance and the features we wanted to use, we also did domain knowledge. We have lot of features that we used to use in our machine learning models. But if you employ all these features in your machine learning models, most of the features might not be very important, or their output towards your model performance will be very limited. So we do not want this. And most of the features also may be highly correlated. So after we have a bunch of features from expert guidance and domain knowledge, we did a stepwise logistic regressions. And in stepwise logistic regression feature selection, we use both backward selection and forward eliminations in order to select what are some of the features that are important or will boost our machine learning performance in our model. So after stepwise logistic regressions, all the variables which are not significant, we remove them and we only input the variables that were significant in our model. So after we finish the stepwise logistic regressions, we also did a correlation test, because maybe the stepwise logistic regressions might select two variables which are significant to our model, but these two variables also will be very correlated. Probably correlation is going to be 1 or something. There is a positive correlation between these two variables. So because if they are correlated, that means the performance that this variable can do is going to be the same performance that this other variable can provide to our model. So we will have kind of duplicate variables which provides no different performance aspect in our model performance. So then we decided to drop variables which are highly correlated. Instead, if two variables are correlated, we will drop one and keep one. Okay, so after we select our features, the candidate features that we'll finally input in our model development. So coming to our model development step 3, we develop the models. And as I said, this study was about to establish the XGBoost model. This is the model that we wanted to develop. And the performance of our model would be compared to the random forest and logistic regressions and see if our models perform better than these two. And as I said earlier, the reason why we bring in these two and not other different models is because random forest is one of the most prominent models used in data science field today. Likewise, logistic regressions. So we wanted to see in a newly developed model, can it perform better than these conventional ones or not? So after we select the models, then we partition the data, because in machine learning, we have to do what? A train test partitioning. So we partition the data. So part of the data will be used for the testing, and the other part of the data will be used for training the models. So when we train the model in large chunk of data, which is 80% of the data will be used to train the models, and the 20% of the data will be used to test the performance of the model after learning from the training. And after we partition the data into training and testing set, we optimize our parameters. In other words, we check the performance of the hyperparameters. Because if we just input parameters by random, then that means probably the parameters might not give us optimal performance. So we use a grid search parameter optimization to see which of the following parameter combination will give us a better performance. In that, we also do tenfold cross-validation and hold-out method. And also we did sampling. Sampling here is small, because in most of the medical studies, or probably just any kind of studies that wanted to use machine learning, we have the positive class, and also we have the negative class. So most of the time, the negative class is always more than the positive class. So that means there is some form of class imbalance. And when you want to run your model on an imbalanced data, the model will give you a good specificity, but poor sensitivity. And this is not your goal. Your goal is your sensitivity to outperform your specificity, or probably it could be a little bit threshold, not far from different equilibrium. So in order to avoid or control the class imbalance, we use sampling, simple minority oversampling technique. So we apply smooth to control our class imbalance during the model development. So when we develop the models, we wanted to evaluate the model, to see the model's performance, to see how our models perform, and then we can make an inference from what our model's performance gave us. So we evaluate our models using accuracy, the specificity, the sensitivity, the F1 score, and then AUROC. So to break this down, the accuracy here will examine what is the accuracy of a model in predicting those with liver cancer and those without liver cancer after they already been exposed to obesity and overweight. And sensitivity here gives us the percentage of the positive class, those who actually have the diseases, that is the liver cancer. And this gives us a proportion of patients who actually do not have the disease. And we also have the F1 score, which is the trade-off between sensitivity and specificity. And finally, the AUROC, the area on the receiver operating characteristics. So this gives us the discriminative capability of how our model can able to discriminate between the two classes, between the positive class and also between the negative class, how our model can able to differentiate between these two classes for us. And after we conclude the model evaluation, now we wanted to visually depict of what our models have done for us, because in our objective, we said we also wanted to see what are some of the variables important in our models that could help us to predict liver cancer among patients with overweight and obesity. So that's why we have conducted the visualization part of our study. So in the visualizations, we use XGBoost and also the random forest model to visualize, to show us what are some of the models that were important in our model. And this is our data source and our study population. How do we select our study population? Firstly, we explained that we got our variables through domain knowledge and from expert guidance, and we apply stepwise. This is the variable selection. But how do we select our features, our variables? First, we draw a timeline of patient selections. And our timeline is divided into cases and also controls. So the cases here means those who actually have the liver cancer. And the controls here means those who do not have the liver cancer. But this is a retrospective study, and that means the data is already available. So we use 2 years of observational time to monitor these patients. That means any patient who have to be enrolled in our study must have at least at least 2 visits, because this patient is going to be followed up later to see if he develops liver cancer in 1 year or not. So during our data pre-processing, all the patients who only visit the hospital once and they did not come back, we remove these patients. And after that, patients with 2 or more visits were followed. And these patients were observed in a period of 2 years. But also remember that when we are following these patients within 2 years, only patients with overweight and obese are being followed. Within this period, if a patient has liver cancer, the patient is removed from our study because we wanted to follow these patients after 2 years. When this patient visited the hospital, the patient is being followed for 2 years. And after the 2 years, we specified our index date. The index date is the time we wanted to start our prediction, or in other words, our prediction window starts from the index date. And this index date is a period of which we will now start to monitor these patients, whether they develop the outcome or not, within 1 year. So after 1 year, if the patients develop the liver cancer or the patient is censored, or is the end of the patient's medical record in the database, is also different story that we will talk about. But our study did not cover that scope. We only have a specific period after the patients have been observed for 2 years, then they are now being monitored whether they develop the outcome of interest, which is the liver cancer or not. So after the index date, now we ask an intrinsic questions, which is the patient developed liver cancer within this period? If yes, then this means the patient is one of our cases. If no, until end of 1 year, this patient is going to be labeled as controls. And here is our exclusion criteria. We do not specify 8 criteria. No, any 8 categories in the database, we are all included as long as they have been observed and they develop liver cancer. But those with prior liver cancer within this period are excluded. And those with BMI of not meeting the threshold, we are also excluded. So after we apply this, we have a total of 35,650 patients with this total visits or total admissions in the database. So when you look at this value, it's more than this value. That means the patient visited the hospital many, many times based on different conditions. And this is how I select our cases. And after we applied these patient selection criteria, 133 patients developed liver cancer within 1 year, and 4,016 did not develop 1 year after being followed for 2 years. Okay, so for machine learning models, these were the hyperparameters we chose, and the hyperparameter selection was done using the grid search, not the random search. We used the grid search to give us the best possible combination of the hyperparameters that could give us the better performance of our models. So for XGBoost, a model that we developed to compare it to logistic regressions and random forests, we use the following hyperparameters. For random forests, these were used, and also for random, this is for logistic regressions, and random forests, these were the hyperparameters used. Okay, so for data analysis, all the statistical analysis and the data pre-processing and wrangling was conducted using R, and the models were built in Python. But initially, we finished analysis of data using R, and then we developed the models in Python, sorry, in R, and then we also developed models in Python to see which of these two programs will yield us the better performance. So unfortunately, because I'm more used to R than Python, so when we develop models in R, and then we also develop the same models in Python, compare their performance, their output, realize that the model in Python performs better than R. So we decided to go with the models from Python instead of R. But all the data cleaning, the variable optimizations, the data wrangling, and everything stops were all conducted in R using the current version. And these are our results. First, we explore the distribution of gender among the patients with liver cancer and non-liver cancer. So from this diagram, majority of the patients with liver cancer are men, and those without liver cancer are also men. And when you look at these features critically, you will realize that when we first started with this one, non-liver cancer, they have been followed for 1 year, and majority of the men did not develop, but also majority of the men developed. So according to different studies, literatures also found out that men are at high risk of developing liver cancer after they already been sustained or risk of having obesity and overweight. But one of my professors asked me, in the Gambia, do you think this is the case? I told him that, well, maybe in the Gambia, I would hypothesize that it's going to be the reverse. Instead of men being the high risk, probably women is going to be the high risk. But this is just my hypothesis. So to confirm this assumption, then we have to conduct a study to ascertain this problem. Okay, so this is baseline characteristics of patients with liver cancer and those without liver cancer. So the variables which are continuous data, we are presented with the median and in the interquartile range. And why do we use the median instead of the average? Before we plot in this variable during the data cleaning stage or data pre-processing stage, we first examine the distribution of each of these variables, because you cannot just jump up and use the median to input the data without the mean, because most people believe that mean will give a better display of the data. But there is one problem that is affecting the mean, which is the extreme values, because mean is sensitive to outliers. So we cannot use mean if the variable is not normally distributed. So we first take the distribution of these variables. After we realize that most of the variables are kind of skewed left or skewed right, then we realize that if we wanted to use the average, then the variables mean value here are going to be affected. So if you give this data to a clinician, maybe the clinician is going to say, well, how can the ALP be 63 in liver cancer and just 59 in non-liver cancer? So you realize that the physicians is going to have a lot of questions on your results, because you use the average instead. And in that average, there are a lot of extreme values. And probably those can be due to programming error or due to coding error and so on. So instead, we sort the data and use the median and then the range within the median set. So for categorical variable, we use the n, that's the total, and in bracket, we have the percentage value. And according to our analysis, all the ones that are bold have been significantly different between liver cancer and non-liver cancer. And we also found that those with liver cancer has higher weight circumference, the BMI, the ALP, the triglyceride, SG-GOT, the creatinine, and so on. And on the contrary, the bilirubin, the diastolic, and the albumin decreases. And this is the performance of a model. So we plot an AUROC, the area under receiver operating characteristics, to see if a model can able to discriminate between a positive and negative class. So from here, we've seen that the XGBoost classifier that we developed, the XGBoost model, the extreme gradient boosting model, performs relatively higher than that of random forest and also the logistic regressions. And this is the specific metrics that we use to also compare the difference between our model we developed and also with random forest and logistic regressions. So we use accuracy input from the training and testing. So this data is what we use to develop our models. And this is what we use to test the performance of our models. We also wanted to see the sensitivity, the probability that our model gives us the true positives. That means those who actually have the liver cancer. And this is 0.94. That means 94% sensitive of a model. So this is a good output. And looking at specificity also shows that our model was able to discriminate and tell us that 93% confident that those who do not actually have the disease, which is liver cancer, really don't have the diseases. And this is the variable important plots. We also wanted to examine which variables are important in predicting liver cancer in obese and overweight patients. So we have age, because age here is significant because the different studies also explore that as the patient age, the person have high risk of developing liver cancer when they already have overweight or obesity. But then our study, because we use the Taiwanese in the Gambia, I think this is different story, because in the Gambia, I think it's very rare that you see someone at the age of 20 to 30 within this range having obesity and overweight and the risk of having liver cancer at the end of the day. Although because of lifestyle changes could also be attributed to these factors. But in Taiwan, it's really common. You see someone at 20s, at 30s who has already been obese or overweight with the risk of liver cancer. It's very common. So our study also shows that gender, the body mass index, the albumin, the diastolic blood pressure, and then the body fat. These are the top 6 or 7 variables contributed to liver cancer among patients with overweight and obesity. But when you look at this model, here it indicates that the waist circumference, the bilirubin, and the SG-GOT, these are liver biomarkers. So the waist circumference, whether you have more waist circumference or less waist circumference, do not really tell the difference if you are at the risk of having liver cancer or not. So this is what our models tell us. But when you give these results to physicians, maybe he will have a different question of what these results mean to him or not. Okay, so we also look at the odds ratio. This is the probability that a person's weight with these specific variables increase the risk of having liver cancer if the proportion is more than 1. So this is an error input. It's 1.23. So age, gender, bilirubin, all highlighted values here we are associated with 1-fold increase in liver cancer risk when they have OR, the odds ratio of more than 1. So when the odds ratio is equal to 1, that means that variable is it doesn't have any causations or correlation to the output, which is liver cancer. So if it is less than 1, then that means that variable is a significant or protective factor. But then here, myself have a very but on this albumin present here, because we know that those with low liver cancer will have, liver cancer will have low level albumin, because this determines your body protein state. So if you have liver cancer, this value is going to be very less. So if our model, if our statistical analysis is telling us that albumin could be a protective factor because of this, for me myself, when I finish these results, I have a very big question on this one, and maybe the clinicians will also question me of what I mean by albumin a protective factor, because patients with liver cancer, if they have low level of albumin, that really signifies their liver state. So if this is a protective factor, that means even if the albumin level is very low in patients with overweight, then that means that do not significantly rings any bell that the person will be at high risk of having any liver complications later in life. So finally, our findings we got from analysis is that when we look at the baseline characteristics, patients with liver cancer has waist circumference, body fat, the alkaline phosphate, SG-GOT, triglyceride, and so on, and also low level of albumin. And liver cancer also was higher among men. And we also found that these variables were independent predictors of liver cancer from the odds ratio table. And we also plot a table that shows about the gender discrimination between liver cancer and non-liver cancer. So we found that age, gender, BMI, albumin, diastolic body fat were the most important variables. And our XGBoost model performed better than random forest and also with logistic regressions. So this means that our model could be used in different kind of studies in order to optimize and see how it performs best compared to deep learning or neural network models. And the strength we thought this study provides is, one, this study is a novel technique. The XGBoost is a novel technique. It's one of the new techniques currently applied in medical research. and the accuracy and then the AUROC of a model was higher than logistic regressions and random forests. Although many studies also ascertained this, but some studies also indicated that random forests performs better than logistic regressions. But our study indicated that the contrary. And also, our study also achieved higher performance when we compare this to previous studies, because our studies, we did not use a lot of comorbidities. We only specifically use the baseline and also the lab values. And another strength we have for studies is that the missing values were not many, but I forgot to explain that. The missing values were not many, but what happened to the missing values? Do we delete, do we fill, or do we just ignore them? Well, in our study, for the missing values, how our management done was we fill the missing values. First, we check the distribution of the data. If the data is normally distributed, that means the mean is 1, and then the mean is 0, and the standard deviation is 1. Then we use the mean to input the missing values. We will calculate the mean excluding the NA. Then when we have the mean value in that variable, we will use a mean to input the missing value in that variable. But if the variable's distribution is kind of skewed left or right, then we will use the median. But before using median, we're also going to assess if there are any extreme values due to coding error or so on. Then if this is uncertain, we will use the median to input the missing values. So but how about if the variable is a categorical variable? We have ones and zeros, 1 presence of digits and 0 not. What do we use? So if the variable is a missing in a categorical variable, we will use the majority class, the mode class. If the majority of that class is 0, then we will use 0 to fill in the missing values. So that's how we manage the missing values. But unfortunately, the missing values were not many in our study, so this was not called a concern in our current study. And the limitations of our study, it's really important to highlight this so that in the future, when we are doing studies, we can also trace our mind on this to do a better thing than what we currently have. So this data, MJ, is actually a private fee-for-service company in Taiwan. So if you wanted to validate and to make our study optimize and stand out, then we have to do a prospective external validation. That means we use a training data from the Gambia, from Taiwan, using this MJ database, but our testing data will be used from the database in the Gambia. So, but we will use different set of features that we use in the training to build the model, and the data we got from the Gambia, we will use that as a prospective external validation data to also use that to validate our models that we develop in Taiwan. Or we can also use a multi-center studies. This is similar to this one, but in this one, all the data is going to come from in the Gambia, but we will have 3 sets. Probably in RVTH, we have a set of data, and then we go to another hospital, we have another set of data, and another hospital, we have another set of data. So the first set of data, we will use that to develop the models. The other one will be used for validation, and the other one will be used for testing data. Then we will check the performance of our models using these 3 set of data. So that's what we mean by the multi-center studies. So when we do these, then our results can be generalized to the whole of Taiwan, because it was certain that the models have a very, very good trade-off. And next one is that some of the biomarkers in our study were not included. Example, the AFP, the alpha-fetoprotein. These are some of the great biomarkers that we can use to detect the presence of liver cancer in patients. But unfortunately, the data sets in the laboratory sets did not have this variable. So these variables were not included. And also, some of the lab variables were present, but if their missing value proportion is more than 30%, we decided not to carry out any imputations. Rather, we just decided to delete these variables from our models. Okay, and finally, we conclude and give some stringent advice to all the youths out there who are currently having obesity or risk of having obesity. That to monitor these, we have some modifiable risk factors that you can control, like regular exercise, and also manage your diet, and drink a lot of water, and do routine medical checkup. All these values are modifiable and can help to prevent you from liver cancer after already being at risk of having obesity and overweight. But there are other factors that you cannot control, like your genetics. Although some people believe that genetics is not something real or factual, because if you control the modifiable ones, the genetics will be easier to control. But anyway, that's also another question in air that maybe someday someone will explore on that. And our findings also highlighted that the presented model can help healthcare professionals in decision making, in decision to make with patients with obesity and overweight, the risk of having liver cancer. Our model can tell a lot of things based on the variables that we currently employed in this study. And finally, facilitate intervention and improve outcomes. And also prognosis that I forgot to mention. Prognosis for patients with liver cancer after being risk of having obesity. So this is all I have for you for today. And thank you very much for listening. Thank you again. So if you have any questions, you're welcome to ask. Thank you.
That insightful presentation.
Okay, thank
We
you.
had we learned a lot from this year. One question I wanted to ask was, why did you decide to use classical machine learning algorithms like random forest, XGBoost, and logistic regression? Why not use maybe Inception Net, some existing model? Well, Inception Net will be used for image classification, but why not use some deep learning models to do your classification or your prediction, as opposed to using this classical or traditional machine learning models?
Yeah, can you hear me? Hello?
Yes, I can hear you. We
Okay,
can hear you.
yeah, okay. Thank you very much for your questions. Actually, the reason why we did not go in for deep learning models to do this study is a guidance from my professor, because currently we have been doing a lot of studies using deep learning, using convolutional neural networks and different updated versions. But because my professor said this is a quick study that we wanted to present in one of the conference, so he said we go with just the simple models to develop and present our findings. But we have done this using the more in-depth convolutional neural networks models in deep learning. But this is just an advice from my supervisor to use the common ones, because according to different literatures, they indicated that these common models have been performing very, very great in classification studies. Because we just completed a study using the regression models of XGBoost and SVM, although they perform better, but we also embedded the convolutional neural networks with two back propagations networks. But because, as I said, the advice was from my supervisor to use these common machine learning models for classification, because from literatures, they have been performing really excellent in discriminating your positive and negative class. So that's why we decided to go with these models. Thank you very much. I hope I've answered your question.
That's, yeah, that's perfect. Thank you. Yes. Any other questions?
Yes. And you want to say something? Yeah, so you can
Yes.
answer.
Good. Yeah.
Um,
Come. You
no,
have
you
to.
can just say
Oh.
rather explain.
He said that the major contributor to liver cancer is based on gender, gender, gender expansion.
Right.
And then he saw a bar chart that those with liver cancer are male.
Most of them.
Males, yes, most of them are male.
Mm.
And those without liver cancer, most of them are male. So it's kind of confusing. I'm confused.
So you're confused a
Yes,
bit.
that those with liver cancer are male.
So Karamo, we have a question here.
Okay,
It's a
go ahead.
student. Yes, from one of your chats.
Uh-huh.
He said he'd show
This one.
some visualization where you said there were more men that suffered from liver cancer,
Yeah.
and then sort of in another instance also, maybe the same one said there are less men that suffer from liver cancer in your studies.
Oh, okay. Let me check that. You mean this
This
one?
one? Okay, the previous one, please.
Okay, there you go.
Yes. Yes.
Okay, because first, because the gender is actually a categorical variable. So when we have to discretize the classes, and then this is the positive class, those with liver cancer, and this is the negative class, those without liver cancer. So when we analyzing the data, the total set of data, we have to filter the data. We keep all those positive and those with the negative. So those with the negative aspect is the non-liver cancer group. So in this group, we check the distribution of gender. So with those with non-liver cancer, after the presence of gender, male were the majority. And then those with liver cancer, this cohort group, male were also the majority. Like this what we have here is a spotted sample of from the main table here. So we can see that from gender distribution, male is 107 from the total 133 patients with liver cancer. So male was 107 and female were just 26 people. And the proportion is 20/80. So in the non-liver cancer group, the total population we have is 4016. And out of these populations, 3,077 people develop liver cancer. And this proportion here happens to be male, and the female aspect is just 23. So that's
Oh,
to explain.
yeah. So Karamo, that would mean you don't have a balanced data set,
Yeah, actually,
right?
because if you look at the positive class and you look at the negative class, the data is highly imbalanced, and that's why I said in our methods here we applied smooth, the synthetic
Mm.
minority oversampling techniques. And this smooth here is going to solve the problem of our class imbalance. This is going to generate a synthetic samples and add it to our positive class in the training when we are doing the data training in the muscle learning model. Because if we do not do this, because the negative class is really more than the positive class, that means our muscle learning is going to give us a better performance of specificity to indicate that our patients do not really have the diseases. But our sensitivity that we are interested in, which is liver cancer, is going to be very small. And this is not the goal of this study. The goal is we have good sensitivity, and even if the specificity is not so good, then we can justify our explanation. But if we do not do any class imbalance, that means our model is going to give us a very good specificity, but low sensitivity. And this is going to raise a lot of questions, especially by physicians. They're going to ask me a lot of questions. Then this model don't have a lot of usefulness, because if we are interested in liver cancer and your model is telling us those who don't have liver cancer, then how do we going to implement this model in a current clinical care practice? And then they will really make sense if they say that. So that's why we carried out smooth analysis. And this is normally done when you are training the data in the machine learning models to make sure that you generate a lot of input data for the training that will balance with the current actual data. But in the testing data, the smooth is not applied. It's only applied in data training, and we train the models with the unseen data from the training to give us our model performance. I hope I answered your question. Thank
Yes,
you.
thank you, Karamo. Yes.
Any other question? Anything you didn't understand and you want further explanation about?
Mhm.
Don't be shy. No question is a stupid question. Yeah? You're all here to learn. I think it's a very good presentation in the sense that it's kind of for you people to see how the scientific method works, right? You know, you want to do a research. You have a research question you want to ask. Is what is causing liver cancer, for instance? Is just gender by the fact that you are a male, you have a chance of having liver cancer than a female, or is it other factors that he has mentioned, obesity and other factors? You have a scientific question you ask, and then you want to come up with how do you go about this? First of all, find it if it has been answered. So they did a literature review to figure out whether people have worked on this before and what kind of questions they have asked, what has been answered, what is known. And then you come up with a plan. Therefore, if you know that now actually there is an area that has not been answered, there's a question that I can try to answer that has not been answered before. So you have a gap that you want to fill in the research community, in the general generation of knowledge. Okay, we're going to create knowledge. So you want to say, okay, there's this gap we want to fill. To do that, you come up with methods. So this is why he had this slide where he explains how they do all these methods. And then they went in and implemented this method. Then he discusses his results for us. So that's the scientific method, and it's exclusively that kind of method. Here is just machine learning, but people that are doing even wet lab experiments, people at hospitals, or this is the method. This is the procedure that we use. All right. So thank you very much for that, Karamo, one more time.
You're welcome.
Question. he was explaining that the more people that get involved in liver cancer is due to age. And he said in Taiwan, like people by the age of 20 start to get obese and they get liver cancer. And he said in Gambia it's different, but he didn't get more into
detail. Why do you think Gambia is different, or are you really sure that Gambia is different?
Thank you very much for that question. Actually, when I was presented, a Gambian in Taiwan also asked me this. Well, actually, I'm from Gambia, and then at least I can tell something about Gambia, because in Gambia, I was working in Sanyang Major Health Center, and then I was there for 2 years, and then I checked in the medical records, the registers, because every month we do the disease updates, see what are some of the common diseases patients have been diagnosed with. But obesity and overweight is something that is really, really rare in the Gambia. Because when I was there, it's very rare that a patient comes and then we check the height and then weight, we calculate the BMI, and the BMI is actually higher. So this is something rare. I don't know for now because I missed to come to Gambia for 2 years, but I'll come in December. So I don't know for now. But before, when I was there, it's not really the case. Like in Taiwan, I was doing my internship in one of the hospitals. When you check the monthly medical records, obesity and overweight, other than cancer, is always among the top 10 diseases in Taiwan. And in the Gambia, maybe currently, but before, I don't think this is the case. But like currently, the world is advancing in the sedentary lifestyle, so probably this could also be one of the factors. But still, I'm not sure there's any study that is done on obesity in the Gambia to also prove that obesity and overweight is one of the problem among the youth. Maybe elderly populations could be questionable, but among the youth, I'm not sure this is a big problem. So this was my take on that.
Right, and the fact is that he is saying this based on evidence. He was at the hospital here, and they were looking at records, and this wasn't the case. Okay, so as a scientist, also you should have at the back of your mind when you make a statement, you should provide evidence. It's not a political statement; it's a scientific statement. So based on his experience, this was not the case then. He was in Taiwan. He went to a hospital, and the records are much higher than what they were seeing here in Gambia. All right, go ahead.
Okay, is it that the youths in the Gambia and the youths in Taiwan, Gambians have more immunity to liver cancer?
That's a good question. So,
Okay.
yeah, saying, if you had the question.
Yeah, can you repeat the question for me, please? Thank you.
Is it some kind of immunity? Like, do you think that Gambian youths have more immunity towards liver cancer than Taiwanese youth?
Oh, okay. Thank you very much for this question. Yeah, okay. So initially, when this hepatitis B and liver cancer stuff all commences, although this was long time in Taiwan, but then when according to one of the history from one of the professors in Taiwan from the hospital, I asked him this question. So he said before in Taiwan, most of the pregnant mothers, when they give birth to their unborn babies, these babies, when they examine them, these babies have hepatitis problem. So then they realize that then if these babies are born and then the incubation of hepatitis virus is less than the date this woman was born. So if this child could be diagnosed with hepatitis, then that means the mother was having hepatitis before the mother gave birth to this baby. So this was the assumption that the Taiwanese medical doctors were having. So now they said now they are going to make the hepatitis vaccine generally accessible to all the newborn babies and to the youth and also to the pregnant populations. Because it's also worth knowing that Taiwan is one of the countries who generally accessible hepatitis virus. So I think it's not about the immunity of the Gambians. So like in the Gambia also, because I was a public health officer in the Gambia, and then I have been given the hepatitis virus at birth and at 2 months and so on, and also with 6 months with pentavalent vaccines with different combination vaccines. So I think it's not about immunity, because before the Taiwanese realized that most of the hepatitis virus was as a result of the liver cancer problem, is hepatitis B and hepatitis C. Then they realized that most of the newborn babies are having this. And then when they realize that because if the newborn baby is born, maybe the virus is still in the body, but it's not totally cured. And when this child grew up at 20s, 30s, and he is obese, there is a high chance that this virus may replicate again and make him. So I think immunity could also play a part, but I think also our lifestyle. Because in Taiwan, the kind of food they have, And in the Gambia, the kind of food we eat a little bit different. It's all contributed, especially to the obesity state. So if immunity also plays a part, then I think the lifestyle also plays a part as well. I hope
Good.
yeah.
Any further question? Was that clear?
Yeah. I think in that case, then they need to add heritage in the thing.
Yeah,
Meaning of your parents having it, then yes. So we have a similar project at MRC where there's a whole group studying hepatitis B,
Okay.
and they would get information about if somebody has it, then they would go to the parents, include their parents, and they collect the sample, like blood samples, and do tests for the parents also. Yes.
Okay.
So, what the question from me is that your research did not focus on the hepatitis B part of the liver cancer problem, right?
Yeah, we explore about the hepatitis B part we did was is different scenario. We explore on why hepatitis B and hepatitis C are one of the leading cause of liver cancer in Taiwan. This is a different study paper that we conducted, and if your question is about hepatitis B and hepatitis C, because currently there is no vaccine for hepatitis C, so the only thing is just prevention. Sorry, just control method, just control it. And for hepatitis B, there is a vaccine. If the person is diagnosed, he will give vaccine. If the person before he is diagnosed hepatitis B, he is given vaccine to protect him from hepatitis B virus. But if he have it, then he'll be given some treatment protocol that he would undertake. But for hepatitis C, there is no current treatment. So the person was given only preventive measures to abstain from it. But we conducted a study on this. It's a clinical trial, but it's still not completed yet for hepatitis C and hepatitis B. Why these are leading cause liver cancer in Taiwan. So yeah.
Interesting. Yes. Ma'am, you have a question? How prone? Right.
Mhm.
Good question. Do you hear it, Karamo?
No, I didn't hear that. Can you help me?
So she said that she understood that your work is to build a model that will predict the person's probability of having a cancer, right?
Yeah.
So have you actually used this to really predict somebody else? I like to say in the next 1 month or in the next 3 months they would have cancer.
No, because after we develop this model, we will give this model to a hospital in Taiwan, and they're gonna use this model to guide them. For example, the looking at the clinical variables here. So when the person will having obesity and also is overweight, then our study predicts that in 1 year, this patient will be higher at a higher risk of cancer. So our model tells us that these top variables here needs to be really monitored if this patient is having obesity and overweight before he will have liver cancer. So this model will be given to a hospital, and they are going to base judgment on our top 10 variables here. And when a patient with the risk, which is the liver cancer and overweight, then he also will be monitored on these issues. So this is completed yet, but it's been approved by the Ministry of Health in Taiwan. So if that is done, then this should be given to the hospital. They will see if they can implement it into their current clinical practice. But right now, not yet.
No, not yet. And normally there's a series of process before these things really happen. It's like building a medical instrument, you know.
Exactly. Yeah. Exactly. Right.
It has to go a series of processes to ascertain that it will do what it's expected to do before it's implemented. Very interesting. Very interesting. Questions? So one thing that should come out is that he is using machine learning to do this, right? And that's why we have this meeting. It's about machine learning models. So you can see the potential of these models. This would have been many experiments by them. But this you have all this data there. You use now artificial intelligence, machine learning, data science, and you're able to do from this. You can see features, the age, the gender, BMI, and so on, being the more important. This is actually from the data and the tools, the algorithm that you use to analyze. So you could be contributing to solving health problems, even though you may not be a medical doctor, you're a computer scientist, right? So this is the whole point here. All right, we don't have any other questions for you, Karamo, but this has been great. I don't know, probably we'll reach out to you. I have an MSc student working on this similar project on the MRC data, but we are looking at hepatitis B, how it progresses to liver cancer or not. What are there indicators that would tell us whether somebody will progress to liver cancer or not progress to liver cancer? So they have like 10 years from 2011 or 2010, they've been collecting this data of patients with hepatitis B. So you might want to talk to me later and see how that relates to your work.
Okay.
All right, thanks. We will have a break.
All right. Thank you all.